So today we'll be discussing the assignment 11 previous year questions. So what is the syllabus of assignment 11? I'll write now. Okay. So in this assignment, we will be discussing some theory related to series DC machine, series DC machine. Then we will see the Swinburne's test. Hopkinson's test. Okay. So first of all, we will be seeing the series DC machine. So before we have drawn the series DC machine, so how it is something like this, that here you have the armature, then here you are having the armature winding and the field winding, which are both series connected. And then here it is connected to a voltage supply. So suppose this is a motor. So it is like this, that here this is IA, which is also equal to I field, which is equal to IL. This is EB. So here we have I field is equal to IA is equal to IL. EB is ZNP phi by 60A. And we know that EB can be written in terms of constant like KN IF. So here we see that IF is proportional to IA and IL. So we can write that it is KN IA also. Okay. Now here, what about this expression? So here let us suppose that this field winding has resistance RF and this armature winding has resistance RA. So this becomes IA is equal to V minus EB by RA plus RF. So these are the basic KCL KVL equation. So this is the basic KVL equation here, because it is in series. So the series with the armature current and field current will be same. Then here we can see that EB is proportional to ZNP phi. Basically, it is proportional to speed and flux, where flux is proportional to field current, or it is also proportional to armature current. Okay. Then what about torque? In the previous class, we have seen that the torque expression for the DC machines is what? We have derived it also. Okay. So this is what it is. Basically K into IF IA. Okay, so it is proportional. So torque is proportional to flux into IA, which is, so here flux is proportional to field current IA, and here I am taking the proportionality constant, suppose KT. Okay, so this is proportional to IF into IA, and we know that it is, so field current is same as the armature current, so it becomes proportional to IA square. Okay, so this is the situation of the torque. So this is the situation of EB and this is IA. Okay. Now here if you see, so here also the same things are discussed, that how the torque is proportional to I square or IA square. Okay. Then if you see here, this is the expression which we have also obtained. If you see, this is the expression we have also obtained. If I write it in a simpler manner, it becomes IA RA plus RF plus EB is equal to V. Okay, so this is the same expression. So here plus EB is equal to V, and we know that EB is also proportional to N into IA. So I'll be writing V as in terms of this, plus EB in terms of EB, I'll be writing the expression of this KN IA. Okay, so what about speed then? So if I derive the speed expression, So we can see that the speed becomes, if you neglect this drop, if we neglect this drop, so neglecting the drop, okay, so we can see that the speed is inversely proportional to IA. Okay, so this is the same thing which sir has also told in his class. If you see his recorded lectures, so this is what he has also derived, that torque is proportional to kt into I square. Here also you see torque is proportional to kt into IA square. Okay, this one. And if you see here from this expression, he has derived that the speed is inversely proportional to current. So here also if you see, the speed is inversely proportional to current. Okay, so this expression, okay, this expression and this expression, they're very important expressions. Okay, and this one also. So you see, if you draw the, because they're inversely proportional, so if you draw the speed versus current characteristics, so what will happen? This characteristics will come out to be a rectangular hyperbola. Okay, because it is inversely related. Now, because this is inversely related, so what happens when there is no load? Because this I current will flow when? This current I will flow whenever there is the load torque. Okay. If there is no load torque, then there will be no current, very small amount of current will flow. Okay. So if you see, if there is no load connected, if there is no load, then this I will be very small. Okay. And when this I is very small, we can see that on this speed axis, on this y axis, the n will become very large. Okay, as you keep on decreasing I, you can see that n keeps on becoming very large. So at very small values of speed, n will be very large. That is why the series motor is not started at no load. Okay, there has to be some load so that the speed does not go to infinite. Okay, so that is why series motor is never started at no load. Okay, there has to be always some mechanical load connected to the series motor so that this I is not near to zero and the speed does not become infinite. So this is also very important points. Okay, so now you see, so first of all, if you see, now we will plot the torque versus IA characteristics for the two machines. Okay, two machines being shunt machine and series machine. Okay, so here we have a shunt machine. So this is RA, this is RF. Here we have V. So this is shunt machine. Now for series machine, it is like this, as we have seen in the previous diagram also, that the windings, the armature windings and field windings are series connected. So this is the case of series machine. Okay. Now we know that what is, we have seen, right? We have derived that first of all, that the mechanical power developed is given as EB into IA. Okay? And we know what? We know that the torque is, so mechanical torque developed is proportional to EBIA by omega, right? Because torque into omega is power, and because we are calculating the torque, so the torque will be power divided by omega. Okay. Now we know in the expression of EB that EB is what? ZNP phi by 60A. So you can say that EB is proportional to phi and N. So N is in RPM. Okay, so similarly, EB will be proportional to phi into omega in radian per second also. By multiplying this 2 pi n by 60, if you do, then you will get omega in radians. Okay, like that. So EB is proportional to KB phi omega, where KB is the proportionality constant. Okay. So instead of EB, I will be putting this. So you can see that here it becomes KB phi omega IA by omega. Omega omega gets cancelled. So mechanical torque developed we can see is KB phi IA, which we say, right, all the time, that the torque, electromagnetic torque, is proportional to phi into IA. So it is coming from here. Okay. So it is coming from here, from all this derivation. Now, for the shunt motor, okay. So for shunt motor, what happens? So we know that phi is proportional to field current, whether it be shunt machine or series machine. Okay. Now here, so here if you see for shunt motor, this torque developed is what? Proportional to KB into IF into IA. Okay. And as long as your field resistance is same, as long as your supply voltage is same, so the field current or flux also remains the same. Okay. Now if we talk about series machine, so for series machine, what is the torque? Torque here also for this is for DC machine. Okay, this mechanical torque developed expression, which is proportional to KT, the proportionality constant, into phi into IA. This is for all the DC machines. Okay, irrespective whether it is series, shunt. Okay, like this. So this is for all the DC machine. Okay. Now depending on whether it is a shunt machine or series machine, the instead of phi we will be putting the things like depending on whatever is the connection. Okay, so here this is, so you know that this phi is proportional to field current, and for this the field current is same as armature current. So what happens to phi? It is also proportional to Ia. So here it becomes proportional to Ia square. Okay, this is for series motor. So torque versus IA characteristics. Okay, if you see torque versus IA characteristics for the two machines, this is the shunt machine, this is the series machine. So you can see that the torque versus IA characteristic. So for the shunt machine, it is what? It is proportional to only IA. If we consider that there is no change in the field resistance, there is no change in the terminal voltage, so this IF will remain the same. So torque will be linearly related to IA. Okay, so it will be like a straight line passing through origin, y equals to mx. Okay, so torque is proportional to IA. Now for this case, torque is proportional to Ia square. Okay, so you can see that the torque is proportional to Ia square. So you can see that the torque developed in case of series motor is more. That is why if you see series motor is also preferred in the case of traction applications also, because the torque developed is huge, okay, for the same, like if you just change the connections like this, so the torque developed will be more compared to the shunt machine, okay. So that is why this series machine is preferred in traction load. And as I said that the series motor cannot be what you say started at no load condition. So because at the time that when the engine is there, it is connected to various coaches also. So you see the train is never started at no load, right? So there is always a load connected. So this is for traction applications, it is preferred. Okay. So here also the sir has also discussed the same thing. If you see, torque is, you can see the what you say linearly related in the case of shunt machine, whereas torque here is what you say parabolic. Okay. Now if there is saturation, if when there is a saturation, suppose, so let us take the case of saturation. So for series motor, torque and IA are what? They are, this is parabolic. But if suppose the field gets saturated means what? The flux becomes constant. Okay. Saturation, what happens in saturation? This flux is not changing with current, right? It becomes constant like this. So flux versus IA characteristics. So flux becomes constant irrespective of the IA value. Okay. This is what I meant by saturation. So let me draw that there so that it is clear. Okay. So flux versus IA. So this is the saturation region. You can see that the flux becomes constant. Okay, even though the IA is changing, flux becomes constant. But in this region, you can see in this region, the flux is proportional to IA. Okay, so when this is getting saturated, so what happens? So before saturation, the torque will become be like parabolic, like torque will be proportional to IA square. But as soon as saturation happens, so what will happen is that this will become now linear, right? Passing through origin kind of a waveform. So that is why if you see in this region, it will be proportional to IA because flux has become constant. Okay, so this is the characteristics of the series motor. Now so how to do the speed control of the series motor? So if you can change the current which is passing through the field, okay, so if you can control the field current, then you can do the speed control of the series motor. So you see sir has discussed three methods. So one of this method is that if you can change the connection of the field windings, okay, so how to do that? And if you connect the diverter resistance, which I will discuss, okay. So here if you see, what happens is that suppose it is a two pole machine. Now in two pole, what we are having? We are having half of the part of the field winding on one pole and other half on the other pole. And it suppose in first case, they are series connected. Okay. So they are series connected. You see here, they are series connected. So when they're series connected, so what happens? This current which is flowing in the armature is the same current which is flowing through both the coils, okay, or both the field winding coils. So in this case, what happens is, because you see, if we, so this is the expression, so let me write. So we know that V minus I RA plus RF is EB. Now, if suppose you neglect this drop, okay, you neglect this drop, so V and EB are almost same. So what happens? Now we know that EB is proportional to what? EB is proportional to K phi omega, right? So V you can write as K phi omega. Okay, so this becomes K phi omega. Now in this case, you see what is the what is the flux? So flux is dependent on field current, and you see that the what is the field current? It is same as the current which is flowing in the armature I. So it is also I. Okay, so you see this is also I. So this becomes what? So V is equal to Ki omega. And if you see omega, so omega will be V by Ki. This is first case, okay, when these two windings are connected in series. Let us suppose if these two windings are connected in shunt, then what happens? So what happens is that this current I gets divided in these two coils as I by 2. So you see the flux, so field current becomes I by 2, right? So by following the similar discussion, V is K phi omega if we neglect this IARF, this resistance drop in the armature and field winding. So this terminal voltage almost becomes balanced by the back EMF. Okay. So V is equal to K phi omega. Now here phi is what? Phi is proportional to IF. So I'm writing IF. This is omega 2. Now in this case, it is I by 2 omega 2. Okay. So what is omega 2? You can see omega 2 is almost double the from the previous case, right? So this is 2 by 2V by Ki. So here you can do the speed control in this way. Okay. So in the one case where you are having the shunt connection, you can get almost the double the speed of the series connection. Okay. So if you have like more number of poles, then you can get more combinations. If suppose there are 4 poles, then in 4 poles, you can either connect all the windings in parallel. This is one connection. So here you will get from this case, and when you are connecting all the windings in series, so you will get almost 4 times the speed, okay, in this parallel connection of 4. Then if you can have another combination being you can have 2 sets of parallel connected coils in series, okay. So in this case, you will get double than this case, okay. So this is how you can do if you are having more number of poles, like 4-pole machine, okay. So this is how you can do speed control by changing the connection in the field winding. You will be seeing there will be some questions also, okay, on this. So we will be seeing that how by changing the field connection, how the field current changes, and when the field current changes, how it also affects the speed, okay. Now, if suppose you connect a diverter resistance, like suppose here you are having, so this is the field winding, and then you have connected a diverter resistance here. So let us say this is R diverter, this is RF, this is RA, this is I, okay, this is I, this is V. So this is by connecting a diverter resistance. So on this also there are some questions, okay, the diverter resistance is connected. So what is the new speed in this case? Okay, all these things are there. So we will see those questions. So here what happens is that first of all, what is the current which is flowing through this field this field winding now? So you will see that the what you say, this current which is flowing to the field winding can be done using this current division in these two parallel connected resistances. So it will be equal to this value, okay. Now you know that if we neglect the losses in the resistive drop, so the terminal voltage gets almost balanced by the back EMF, which is equal to K phi omega. Now we here K is, we are taking a proportionality constant, and phi if we take as proportional to field current. So this is IF omega. So what is IF? IF is now I into R BEF plus R diverter. Now in the previous case, without R diverter, what is this speed? So it is KIF omega. So because this current is the same as current which is flowing in the armature winding, so in that case it will be KI omega. Okay. So this is the situation. Now what is the omega now? So omega 2, let us say this is omega 2. So omega 2 becomes proportional to RF plus R diverter by R div by Ki. So if you can vary this R diverter, you can vary the speed. So this is how by connecting a diverter resistance, you can get variable speeds. Okay. So this is the doing speed control by connecting diverter resistance. Okay. Now we will see the two tests which I said, Swinburne's test and the Hopkinson's test. Okay. So here let us see what are these two tests. So first we will see the Swinburne's test. Okay. So what is the purpose of Swinburne test? It is used to calculate constant losses in the machine. Okay. So here we can, like, without actually loading the machine, we can calculate efficiency. Okay. So that is why, because we are doing it without actually loading the machine, so this method is also known as predetermination of efficiency. Okay. So here how it happens is, so let us see how the Swinburne's test works. So here, let us suppose we are connecting a machine, remember a shunt machine, okay? Because we are doing this machine at this test at no load. So this is a no load test. So we know that we cannot run a series motor at no load, right? We have seen what is the problem of running the series motor at no load. The speed becomes infinite. So this test can only be done on shunt machine, okay? Not on series machine. So here, this is the shunt machine. Now here, this is the so this is the connection. So this is the armature winding. Just say this is the armature winding. Okay. Having the resistance RA. Okay. This is the field winding having the resistance RF. And this is the voltage V. Now let us say at no load, the no load means there is no mechanical load connected. Let us say at no load, this motor is taking current IL0. Okay, this is the current IL0. Now here what will be so the armature current here we are taking it as IA0, and let us say this is ISH. Okay, so what is the input? So input power of motor is V into IL0. Okay. Now what happens is that because we have not connected any load, so whatever power is being taken, because output is 0 at no load, so whatever power is taken, so input minus output, this becomes equal to losses, right? We know that what is input? Input is output plus loss. But because at no load the output is 0, right? So let me write it as output and input. Okay. So this is input minus output. So we know that for no load, the output is 0. So this is, we know, and what we know is that input consists of output plus losses. So here input minus output will give out to be loss, but because the output is 0 in this case, so input becomes whatever input you are providing to the motor, that is being required to meet all the losses. So what are these losses? So first of all, you have iron loss, okay, you have mechanical loss, then you have copper losses. So what are the two copper losses? So you have, first of all, copper losses Ia square Ra, and the another copper loss in the field winding is ISH square RSH. Okay, so these are the constant losses. These are variable losses. So what happens is, as you change the, what you say, current, you see these, because as you change this IA, this load current, this armature current changes, and hence the shunt current also changes. So that is why these are variable losses. Okay, it depends on the loading. Okay, as the load changes, the current changes, and hence these copper losses or variable losses changes. Okay. Now you see, from this Swinburne's test, what we do is we find out what is the, what you say, constant losses. Okay, so here I'll write it. So here, if you will see the ISH square RSH loss, if you see the in the copper loss of the field winding, if you see, it is not a variable loss. Can you tell me why? Because this, if the terminal voltage remains the same, so you see what will happen to this because the shunt current will be the same, V by RF will remain the same, and hence this ISH square RSH is also comes in the constant loss. Okay, so only variable loss is Ia square R, this armature copper loss. Okay, so this is the only variable loss. This is also comes under constant losses only. Okay, so here, so if I have to find out the constant losses, it becomes equal to what? It becomes equal to the input power. So input power minus, so this losses consist of all the loss. So this consists of what you say, variable loss plus constant loss. So from constant losses, what I have to do, I have to subtract the variable losses from the input power. So what is the variable loss? It is the, what you say, I is 0 square Ra. Okay, so in this way we can get the constant losses. Once we get the constant loss, we can use it to determine the efficiency. So how you will determine the efficiency? So let us suppose in the new case, now let me put another slide. Okay, so let us write application of Swinburne's test. So now from the Swinburne's test, we have the constant losses. Now let us suppose we have now loaded the machine and we now to calculate the efficiency of the loaded machine. Okay, so how we can do is we can do it like this. So let us suppose now you have loaded your machine. So this is now IL. Okay, so IL 0 means no load. IA 0 means no load, but IL and IA means on loading. Okay, under load. This is ISH. Let us suppose this is V. So in this case, what is the input power at loading? Okay. So input power in this case is voltage into current, VIL. Okay. So this is VIL. Now, what about the variable loss? As I have discussed, the variable loss is what? Copper loss in armature winding. Okay. So let us suppose this armature winding has resistance RA and field winding has resistance RSH. Okay. So what about variable loss? Variable loss is the copper loss in armature. So it becomes IA square RA. Okay. Now, what is output power? We know output power is nothing but input power minus losses. So what are the losses? So one loss is the what you say, this variable loss, and one is component is the constant loss. So constant loss we have already obtained from the previous case, right? From the no load condition. So this is the constant loss which will be taking from the no load. So constant losses remain the same whether it is on load or without load. Okay. Because the change in the speed is not that much. Because if you apply the same terminal voltage, so the flux remains the same. So flux remains the same, and also the speed is also does not change that much. Okay. So you will see that the iron loss and mechanical loss will almost remain the same. And we can see that because this is a what you say shunt connected winding. So if you're not changing your terminal voltage, so shunt current is also same. So shunt current is same means even the what you say copper loss in the field winding also remains the same. Okay. So now this is the situation. So here we can get it like this. So input power minus variable loss from loading, so IA square RA, and constant losses from the previous case. Okay, so constant losses is nothing but V into IL0 minus IA0 square RA. Okay, so in this way you can get output power. And what is efficiency? Efficiency is nothing but output power by input power. So in this way you can calculate the efficiency. Okay, at any loading condition. So now we will see what is the Hopkinson's test. This is also called as back-to-back test. Okay. Here what happens, we connect two identical, what you say, this is used for shunt machine and compound machine. Compound machine we will discuss in the next class, but I am just writing. Okay. Used for shunt and compound. Okay. So in this machine also, so what we do is we connect two machines, identical machines back to back. Like one machine will act as the motor and other machine will act as the generator. So let us say this is the machine. So let us say this is the first machine, which is acting as the motor. Okay. It is mechanically coupled to another machine, which is acting as, let us suppose, generator. Okay. So ideally what should happen, that the what you say, the motor and generator exactly load each other. So what will happen is, in this condition, whatever power which you are supplying from the outside, okay, that power is, what you say, being taken for meeting only the losses. Okay, so let us say this is current I2. So this is the power. So this is the V into I2. This is the total losses in motor generator set. Okay, now let us say that the generator, because generator will give the electrical output, so let us suppose generator is giving out the electrical output in the form of electrical current as I1. So V into I1 will become electrical output of generator. Now what about motor? If you apply KCL here, the motor will take the current I1 plus I2. So V into I1 plus I2 is input of the motor. Okay, and we know that the output of the motor, which is the mechanical output, is same as the input of generator. Okay, so what is the efficiency of the generator? So efficiency of generator is output power of the generator divided by input of generator. Now output of generator is V into I1. And what about input of generator? Input of generator is output of motor, right? So here it is output of motor. Now, what is the output of motor? We know that the, if we say motor efficiency is nothing but output of motor by input of motor. So output of motor is nothing but motor efficiency into input of motor. So I'll be writing that. Okay. So this is nothing but efficiency of motor into input of motor. Okay. So this is nothing but V into I1 by efficiency of motor. And we have seen what is the input of motor. It is nothing but V into I1 plus I2. So here if you see this efficiency of generator into efficiency of motor is I1 by I1 plus I2. Okay. Now here we have to, if we say total loss in both the machines, so it is nothing but rotational loss plus copper loss. Okay. So what is the rotational loss? So rotational loss is nothing but the total loss. So total loss is V into I2, which is the power which is being taken by the motor to meet the losses. So it is V into I2 minus the all the copper losses. So copper losses in each of the, what you say, it's armature windings, in each of the field windings. So let me just draw those. So here it is like this. Okay. So let us say this is I3, and here in the we have RA. So this current becomes I1 plus I3 in RA. Okay. So, okay, just let me draw this neatly again with the all the, what you say, mm, windings separately. Okay. This is motor. Now for the motor, we have field. So this is the motor armature, motor field. Okay, so let us say RFM, RAM. This is motor. Now it is mechanically coupled to the generator. Okay. Now here also we have armature winding with having Rag resistance. And here we have field winding having RFG resistance. Now current being taken was I2, right? Now here current coming out was I1. Now let us suppose the current flowing in the field winding of the generator is I3. So current which is flowing through the armature winding becomes I1 plus I3. Now here current here is I2 plus I1. Okay. Now let us suppose this current is I4. So current in the field armature winding of the motor becomes I2 plus I1 minus I4. Okay. So here the rotational loss is Vi2 minus total copper loss. So this is Vi2 minus what is the copper loss? So copper loss in the armature winding of the generator. So I1 plus I3 square Rag. Then in the field winding of the generator minus I3 square RFG minus the what you say field winding of the motor. So let us say If square RFM minus the armature winding of the motor. So this is plus, basically minus is taken common out. So this becomes I2 plus I1 minus I4 square RAM. Okay, like this. And you see this is the rotational loss of both machines. Okay. So let us say this is RPR. Okay. So rotational loss of individual machine, because they are identical machines, so rotational loss of each machine is around PR by 2. Okay, so in this way you can write. Now efficiency of generator is what? Efficiency of generator we have seen. What is the output of generator? V into I1. So this is output by output plus losses. So what is the loss in the generator? So because the rotational loss in the generator is PR by 2 plus the copper loss. So what is the copper loss in generator? I1 plus I3 square Rag plus I3 square RFG. So this is the efficiency of generator. And what about the efficiency of motor? So input of the motor is V into I1 plus I2. So we will write in the input. And what is output? Output is input minus loss. So what are the losses? So here also the loss is, the rotational loss is PR by 2 plus the loss in the winding. So here we have the copper losses in both the windings. So here we have the loss in the field winding plus loss in the armature winding. Okay. So this is the efficiency of the motor and efficiency of generator. Now we will see the questions one by one. So in all of the questions, you have to consider, you will see in general for the series motor, you will be considering two equations. One is the equation of torque and one is the equation of back EMF. You will be using these two equations to solve the questions. Okay, this is what you will see in all the questions. Okay, so here they are saying a 240 volt DC series motor has armature resistance 0.3 ohm and field resistance 0.4 ohm. It is running at 500 RPM while drawing 10 ampere current. The load torque is constant. And they're saying the magnetization curve is linear. Linear means it is not saturated. So they're saying that the torque proportional to phi into Ia. So here phi is not saturated. Okay. Now what they have done is that they have connected a 0.6 ohm diverter in parallel with the series field. Okay. Now this is the case. So let us draw the two cases. So in one case, which is the initial 10 ampere case. So in this case, we have, this is the armature winding. This is the field winding. Now the armature resistance is 0.3 and field resistance is 0.4. Okay. So the machine is drawing 10 ampere current. Okay. So this is one condition. Now the other condition is like this. So here in the field winding, you have connected a diverter resistance. Okay. So RF is 0.4. R diverter is how much? 0.6 ohm. And RA is 0.3 ohm only. Okay. Now let us suppose this new current is I2. Okay. Now what we need to find is, we need to find the new speed. So old speed N1 is 500 RPM. Now we have to find out N2. So as I said, we will be using the two equations, torque equation. They are saying the load torque is constant, means the torque in both the cases, in the first case and in the second case, the torque remains constant. So in the first case, what is the torque? Torque is proportional to flux into Ia. Okay? So flux into Ia. Now in the previous case, the flux is proportional to field current and field current is also equal to Ia. So this is nothing but Ia square. So torque is K Ia square, let us say. So this is K into 10 square. Okay. Now in the next case, what is the torque? Torque is proportional to flux into Ia. Okay. Now here we are saying that let us say the Ia is I2 and flux is field current proportional to field current. Now what is the field current when you have connected the diverter resistance? You see this is the field current as I discussed here. So new field current becomes I into R diverter by RF plus R diverter. Okay, by applying the current division rule in the two parallel connected resistance. Okay, so this becomes IF becomes I2 because here current is I2 into R diverter by R diverter plus RF into I2. So in this case, the torque is K I2 square into R diverter. R diverter is 0.6, 0.6 by 0.6 plus 0.4. So it is 0.6. Okay, 0.6 plus 0.4 is 1. So like that. So these two torques are equal. This is one equation you have. So K into 10 square is equal to K into I2 square into 0.6. So from this you can calculate the I2. Okay, so you will see that the I2 will come out to be 12.9 ampere. Okay, so this is how you will solve the current using the constant torque expression. Now so you see the next question, they're asking that what is the new motor current in this. So in the new motor current, you can just find by using only this part. So you will see that the next question is already solved. Okay, if you calculate for this. Now what we have to do is we have to estimate the speed. So how we will do the speed? As I told, we have already used the torque equation. Now we will go to the back EMF equation. Okay, so what is the back EMF? We know that the back EMF is proportional to phi into omega, K phi omega. So back EMF for the first case is proportional to K IF omega. So in the first case, the IF1, let us say IF1, so it is proportional to IA only, K into IA into, and what is the speed? Let us say this is 500 RPM. ठीक है. Omega you can write it in 2 pi n by 60, but because it is all this is all proportional, and then we'll be using the what you say divide the two back EMFs. So in that case, this constant will get cancelled. So don't worry, even if you take it in RPM or radian per second, it's okay. Okay, you don't need to convert it to radian per second. Now this is K into IA into 100. So this is K into 5000. Now what is EB for this case? So EB for this case is V minus IA. So this is V minus IA into RA plus RF. This is EB in this case. So here EB is V minus, so voltage is कितना है 240 minus IA is 10 into RA plus RF is 0.7. ठीक है. So EB comes out to be how much? EB comes out to be whatever value. ठीक है. So this is 240 minus 7 means 233. ठीक है. This is proportional to K into 5000. Let us say this is equal to K into 5000 because K हमने already ले लिया है, K into 5000. अब दूसरे केस में क्या होगा? EB2 is equal to K into IF2 into omega. ठीक है. और हमें पता है कि हमारा IF2 कितना है? IF2 तो है हमारा I2 into R D what you said this क्या है ये डाइवर्टर by R डाइवर्टर plus RF. ठीक है. तो ऐसे करने से देखोगे कि तुम्हारा I2 जो होगा ये होगा IF2 जो है I2 into 0.6 है. ठीक है. मतलब 12.9 into 0.6. तो ये हमारा I2. तो हमें क्या करना है यहाँ पे IF2 है ये, तो IF स्क्वायर नहीं है, IF2 है. ठीक है. ये कंफ्यूज नहीं होना कि दिस इज स्क्वायर. ओके, दिस इज IF2. ठीक है. तो EB2 हमारा इस केस में क्या है? EB2 है हमारा V माइनस IA. ठीक है. तो एक केस में है हमारा माइनस ऑफ I2 इंटू इन दोनों का पैरेलल कॉम्बिनेशन प्लस सीरीज कॉम्बिनेशन. दिस इज I2 और ये R डाइवर्टर पैरेलल RF प्लस आर सीरीज. ओके, ये है हमारा EB2. ये हम लोग कैलकुलेट कर सकते हैं आर डाइवर्टर और RF को पैरेलल करके प्लस आर सीरीज. इन सब में से जो करंट जा रहा है वो I2 जा रहा है. ठीक है. इन दोनों को पैरेलल करके जो रेजिस्टेंस आएगा उसमें से तो I2 ही जाएगा ना, तो इसलिए पैरेलल करके भी I2 ही लिया है हमने. और ये है इक्वल टू K into IF2 which is equal to 12.9 into 0.6 into what? This is omega 2 which we have to find. ठीक है. तो इन दोनों इक्वेशंस को हम लोग इक्वेट करेंगे तो इसमें देखोगे कि हमें ये सब कुछ पता है. यहाँ पे इसको कैलकुलेट कर सकते हो, एक वैल्यू आएगा, ये हमें ऑलरेडी पता है. तो अगर हम इन दोनों इक्वेशंस को डिवाइड कर देंगे तो यू विल सी कि दिस K एंड K विल गेट कैंसर. सो यू विल गेट समथिंग लाइक दिस. ओके. तो हम लोग, और हमें पता है कि ये क्या कहते, तो K कैंसल आउट हो जाएगा तो हमें जो भी मिलेगा इसको यूज करके ओमेगा 2 में मिलेगा जो कि अननोन है. ठीक है. तो इस तरह से ओमेगा 2 हमारा आरपीएम में आ जाएगा. ठीक है. क्योंकि हमने यहाँ भी 500 आरपीएम में लिया तो ये ओमेगा 2 भी आरपीएम में आएगा. ठीक है. तो इस तरह से हम we can find out the omega 2 in RPM. So you will see in all the questions you will be using only the two equations, torque equation and EB equation, either for finding out this new speed or for finding out the new current. Okay, whether by connecting the diverter resistance or by making the windings in parallel. Field windings in parallel हमने किया था यहाँ पे. ठीक है. Field windings in parallel like this. So you will see in all the questions you will see something we will do and then we will be coming back to these two equations. Okay, ये this question we have already solved क्योंकि यहाँ पे भी motor current जो first part में निकाला उससे निकाल लिया हमने. ठीक है. Now we go to the next question. Now in this next question again it is said that so here it is saying that DC series motor has 0.4 ohm resistance and it is driving a fan at 500 rpm while drawing 20 ampere current from a 230 volt supply. The load torque is proportional to the square of speed. इन्होंने बोला है कि अब ये जो load torque है वो जो है स्पीड के स्क्वायर के प्रोपोर्शनल है. ठीक है. सो स्पीड के स्क्वायर का प्रोपोर्शनल है. एंड we have to change the speed of the motor to 600 rpm by controlling the supply voltage. Okay, so what is the new supply voltage? So they are saying that instead of putting a diverter resistance or by making a parallel connection in the field winding, we will be changing the supply voltage only. That we can always do, right? When we change the supply voltage, then the current drawn will change, and when the current drawn changes, then the speed changes, right? That we can always do. So that is what we will be doing here. So what we will do is we will be changing the supply voltage. So we have to find out the new supply voltage. So what is the torque? So torque is proportional to phi into Ia. We have seen it is proportional to phi into Ia, right? Now you see, because it is a series motor, so it is a series motor, so for now we are not putting any diverter resistance, we are not making the field winding parallel or anything like that. Okay, so in that case the Ia will be same as If. Okay, so flux which is proportional to If, so it is proportional to If into Ia, which is proportional to Ia square. ठीक है, Ia square और लोड करंट स्क्वायर. तो अब क्या है हमारे पास अब हमें अब मैं जैसे बताया, हम दो इक्वेशंस यूज करेंगे, एक तो टॉर्क का इक्वेशन यूज करेंगे और एक बैक ईएमएफ का इक्वेशंस यूज करेंगे. ठीक है, तो ये दो इक्वेशन देखोगे कि सीरीज मशीन के सारे क्वेश्चंस में यही दो इक्वेशंस यूज करते हैं. ठीक है, सो हियर this is the case. Now another thing is they are saying that the linear magnetic circuit has to be assumed. Like linear magnetic circuit assumption means कि यहाँ पे हमारा जो flux जो है वो saturate नहीं हुआ है. तो अगर flux saturate नहीं हुआ है तो flux will be proportional to Ia. अगर flux saturate हो जाता है तो flux constant हो जाता है. ठीक है, तो torque will be proportional to only Ia in that case. Okay, तो अब क्या है? So now we will see that so in the first case so we will be taking the ratio. So in the first case, the torque TL1 is proportional to Kn square, which is also proportional to Kis square. Okay. Now let us say this is torque 2. So torque 2 is proportional to N2 square. Let us say in the second case, the current drawn is I2. Okay. So this becomes I2 square. So if I take the ratio of two torques, so this becomes N1 square by N2 square is equal to Ia square by I2 square. अब हम लोग देखेंगे तो in this question the speed N1 is 600 rpm by N2 square, and in the first part the current is Ia is 20, so this is 20 square by I2 square. So here we have a relation. So if you see, we have a relation of N2 and I2. Okay, this is one relation. Now we will get the another relation of N2 and I2 using the back EMF expression. Okay, so what is the back EMF? So old back EMF, so EB1 is what? EB1 we can find V minus IA RA plus RF. So what is the supply voltage? It is 230 volt minus IA is 20 by RA plus RF. So this is 0.4 only. Okay, they have said that the collective resistance is 0.4. So this is 0.4. So this will come out to be some voltage. Now what about EB2? So EB2 is proportional. So EB1 is proportional to K phi 1 omega 1, and EB2 is proportional to K phi 2 omega 2. So phi 1, because it is a linear magnetic circuit, so for a linear magnetic circuit the phi is also proportional to If, and If is equal to Ia for a series motor. So this becomes K Ia1 omega 2, and this is K I2 omega 2. Okay, so this is the situation. Now here, so from here you see, in this case we have to change the speed of the motor to 600 rpm. तो N2 जो है वो हमें पता है, N2 is given as 600 rpm. Okay, so from this we can so this N2 is 600 rpm and N1 is 500. Okay, so this is 500 square by N2 is 600 square. So using this we can calculate I2. Okay, so I2 we can calculate, which is 24 ampere if you calculate it. Okay, so this is how you can calculate I2. अब हम लोग क्या करें, वी आर डूइंग द नेक्स्ट केस. अब हम लोग को व्हाट वी हैव टू फाइंड, we have to find the supply voltage. But how we can find the supply voltage? So for that we first need to calculate the back EMF for the second case. Okay, so here you see this is K into I. So in first case the back EMF is proportional to K phi omega. Phi is proportional to IA for a linear magnetic circuit in DC series motor. So this becomes K into IA omega. So IA first in the first case was 20 ampere and omega in the first case is 500 rpm. Now in the second case, EB2 and EB1 we know by solving EB1 is equal to V minus IA RA. This comes out to be 222 volt. Okay. Now in the second case, this is what EB2 is K phi 2 omega 2. So K into I2 omega 2. So because phi is proportional to current only. So I2 we have found out from the this torque equation as 24. So this is 24 into omega 2. Okay. So omega 2 is also known as 600. So from this equation, if we take the ratio of these two, EB1 and EB2, so we get EB1 by EB2 is equal to 222 volt by EB2, which we have to find. And on this side, the K's get cancelled. Okay. So this is 2500 by 24 into 600. So using this cross multiplication, we can get EB2. So EB2 is what you say, you will see it will come out to be 319.6 volts. Okay. So this is the EB2. Now we have to find out the supply voltage. So we can easily find it. What is V2? V2 will be EB2 plus IA2 into RA or RF. So this is RA plus RF. So EB2 we have found from this equation. So this is 319.6 plus IA2. So we have already found it is same as I2. So I2 is 24 and RA plus RF is 0.4. So from this we can find out the value of supply voltage, so that we can run this motor at a new speed of 600 rpm. Okay, this was an easy question. Here what we did, we first used the torque expression because torque is proportional to square of speed, and we know and we also know that torque is proportional to square of current in the case of series motor. So by using that, so we know that, okay, the speed in the first case is this much and the speed in the second case is this much. Then we knew that, okay, the armature current is what you say in the first case is 20 ampere. So by using this expression, we can find out the armature current in the second case required for the 600 rpm case. Now, once we know the what you say, so we have the information of armature current, or which is also same as the field current. Now by using the back EMF equations, so back EMF in the first case we can find out by using V minus of voltage minus this resistance drop. So we get a back EMF for the first case. Now we know the back EMFs in both the cases is proportional to phi into omega. Okay, so omega is known in both the cases, and phi, which is proportional to the field current, is also known in the both the cases, because 20 ampere is given in the question and 24 ampere we have found from here using this cross multiplication, right? So this is, so we get the what you say current in both the cases. Now by using the back EMF ratio, you can get the what you say value of the new back EMF in the in the second case. Now once we know the new back EMF, so we know the new back EMF and then we already know the current. So using that back EMF plus this current resistance drop, we can calculate the supply voltage which is required. Okay, so this is an easy question only. Okay, now in this question we have to find out the current which will be drawn by the motor after so this is the same thing, but here because we solved for the current also and we also solved for back EMF and supply voltage, so in this question they're asking the because it is a sub part of this only, so they're asking what is the value of the current, so which we have already found the value of current for the new case, right? Assuming linear magnetic circuit. So remember this, okay, assuming linear magnetic circuit, it is very important. अगर ये नहीं दिया हुआ है तो it like if it is mentioned it is saturated and then you're solving for linear magnetic circuit, then your answers will be wrong. Okay, this is very important. So so the 24 ampere this current required for the second case we have already found out. So this is the answer also for this question. Okay, Now we go to the next part. Now in the next part of the same data, in the same data, what we have to do? Now we have to solve for the saturated magnetic circuit. Okay, this is important. Okay, ये ध्यान से read करना है. If you are not read this and then you are solving for the linear circuit, like अच्छा series motor, तो series motor में तो torque is always proportional to Ia square. If you do this, then your answer will be wrong. Okay, for this case, what you have to do is, so here torque is proportional to, as I have said, torque is proportional to phi into Ia. Now because the this magnetic circuit is already saturated, so torque will be proportional to only Ia. Okay, so the new torque, so if you say old torque is proportional to Ia, which is proportional to square of the speed. Okay, so they have said that the torque is proportional to square of the speed. So let us say this is proportional to the square of the speed k into, so let us say this is k, k1 Ia, this is k1, k2, and this is uh, proportional to speed square. So the initial speed for the first case is 500 square. Now the new torque is proportional to flux into Ia, where flux is constant, when it is proportional to k1 into I2 which we have to find. And here this is the new speed is 600 square, because the torque is also proportional to speed square. Okay, so using this we can calculate the value of I2. So I2 value is 600 into 600 into Ia, 600 square into Ia by 500 square. Okay, so Ia is given in the question, it is given as 20 ampere. So we will get the value of I2. In the next question, if you see, they are asking us to find the value of current which will be drawn by the motor, ठीक है, assuming a completely saturated magnetic circuit. तो ये जो we have found this I2, we can use, this is the what you say answer required for the next part also. Okay, now we will be using this I2 to find the required supply voltage also. Okay, so here also we will be using again the back EMF equation. ठीक है, अब back EMF is also proportional to what, phi into omega, but this is saturated means phi is constant, so back EMF is proportional to only omega. Okay, so this is very important. If you are solving it in a linear circuit, then you will put, okay, phi is proportional to field current, and for a series motor field current is proportional to Ia, then you will put Ia here, so it will come out to be wrong. Okay, so saturated means the flux is constant. Okay, so you will be taking, so you will be, when you are dividing the two situation back EMF, so this constant flux will get cancelled. So back EMF in that case will only be proportional to omega. Okay, so now what is EB1? So EB1 we can find out. So EB1 is V minus IARA. ठीक है, V minus, so V minus IARA. Now what is V? V is given as 230 minus 20 ampere into 0.4. So this is 222 volt, which is proportional to phi into omega, where phi is constant. It is proportional to omega 1. Now what about EB2? EB2 we don't know, because supply voltage we have to find out in this case. So we cannot tell the EB2 using the supply voltage. Okay, so how we will do is, we know that, okay, it is equal to V minus Ia2 Ra, which we don't know, because we don't know what will be the V2 in this case. Okay, but it is proportional to omega 2. So omega 1 we know as 500 and omega 2 we know as 600. So if we take the ratio of the two cases, EB1 by EB2, we get it as 220 by EB2 is equal to 500 by 600. So if we do this, we will get the EB2. So new EB2 is 266.4 volt. Now once we know EB2, so we can calculate what is the V2 required. So V2 will be EB2 plus Ia2 Ra. Okay, now what is EB2? EB2 we have found out from here. This is 266.4 plus I2 is 28.8 into RA is 0.4. Okay, so if you do this, you will get the value of V2 supply voltage required when the magnetic circuit is saturated. Okay. Now this we have already seen. This was the sub part of this question only. Now we go to the next question. Now in the next question, what it is saying is that an 8-pole DC series motor has 8 field coils connected in series. It is having 8 field coils. Remember, it is like 1 coil, 2 coil, 3, 4, 5, 6, 7, 8. So like this 8 coils are there for the field winding. Okay. And then there is a armature winding. Okay. Now here it is like this. So first of all, they're connected in series. So in the first case, it is connected in series. Now they are saying that it is driving a fan. It was drawing, in first case, it was drawing 35 ampere and the speed N1 was 600 RPM. Now they're saying that the load torque is proportional to speed square. Okay, so load torque 1 will be proportional to N1 square, and in the second case we will see it will be proportional to N2 square. Now what is the second? Now they're saying the magnetization curve is linear. Okay, now in the second case, what we have to do is the 8 field coils are reconnected in 2 parallel groups of 4 in series. Okay, so now it is like this. 2 parallel groups of 4 in series like this. So this is the new situation. Now in this case, what we have to do is we have to find out the new speed. What will be the speed N2? So first of all, let us suppose this current is I2. Okay, now what will happen to the field? So here the field current IF and I1 are same. Okay, but here the field current is equal to half of I2. We have discussed it, right? So now here this is, let us say, RA. So from the torque condition, we know that the torque is proportional to phi into Ia and phi is proportional to IF into Ia. So load torque 1 is proportional to IF into Ia, and IF and Ia are same in first case, so it is proportional to I1 square, whereas the load torque is in the second case is proportional to IF into Ia, but IF is half of the I2. Okay, the armature current. So this is like this. So these are the two load torques. Now here, so we have the one set of equation like this. So we will take the ratio of load torques. So in the first case, we will be getting N1 square by N2 square, which is equal to I1 square by I2 square by 2. Okay, so N1 is known and I1 is known. Okay, so what is N1? N1 is 600 square by N2 square, and I1 square is what? 35 square by I2 square by 2. Okay, so this is one equation in N2 and I2 by 2. Now what we will do is that here now we will use the another equation of back EMF. Okay, now what is the back EMF? So back EMF is proportional to what? Is proportional to phi into omega. Now for the first case, EB1, it is proportional to, because phi is proportional to field current IF, and IF in the first case is proportional to I1. So this is I1 into omega 1. Okay. Now in the second case, EB2 is proportional to IF into omega. Now IF in the second case is halved, okay, because of this parallel connection. So this is I2 by 2 into omega 2. So if I take the ratio of these two, EB1 by EB2, okay. So this is equal to I1 omega 1. So I1 into 600 by I2 by 2 into the omega 2 which we have to find out. Let us say N2. Okay. So this is the case. Now you see here, if you see this, that the load torque is this is like this. So in this case, what we are doing is that we are saying that the actually in the question they should have mentioned somewhere that the back EMF will remain the same. Okay, so this information they have not given, but they should have given. Okay, but they are using that condition. Okay, so that condition they should have mentioned that the back EMF in both the cases will remain the same. Okay, so here if you see the, if you make the back EMF the same, so you will get another what you say condition of N2 and I2. So you have one condition of N2 I2, and then you have another condition of N2 and I2. Okay, so if you use these two conditions, you can find out the value of N2, you can find out the value of I2. Okay, so in this case you will see that okay, so I will tell you that how they have considered the back EMF to be same. They are saying that all the losses are negligible. Okay, so all the losses are negligible means they are assuming that the drop, losses means drop, right? So the drop drop in the armature what you say armature winding and the field winding is negligible. Okay, so the loss or the drop is negligible in this case. So what is happening, because the back this terminal voltage is same in both the cases, and if you are neglecting the losses, basically EB minus IA RF1 plus RA, and V is equal to EB minus IA2 RF2 plus RA. So they are saying to neglect the losses. So neglect the losses means in both the cases this voltage, because V remains the same in both the cases. So like that they have taken the condition that okay, the back EMF remains the same in both the cases. Okay, like this they have said. So if you take that condition, then you will get, you have two equations and two unknowns. So you have one equation from the load torque and you have one equation from the back EMF. So N2 I2 is also a variable here and N2 I2 is another variable here, but you have two equations. So you can solve it, then you will get the value of N2 like this and I2 like this. Okay, so in this question they are asking the new speed, and this question they are asking you the new motor current. So from solving the two equations you can solve the two questions. Okay, simultaneously two questions. Now here they are saying that the same so now this is a 220 volt DC series motor which is having a total resistance armature plus field of 0.4 ohm. So it is like this. Okay, so here this is a series motor. So this is whole is 0.4 ohm. So it was taking 40 ampere. Okay, so I1 is 40 ampere and it was driving a load at 600 rpm, and it is saying that the load torque is proportional to N1 square, and we know that it is also proportional to flux into IA, and because the magnetization curve is linear for the first case, so it is also proportional to I1 square. Okay, because field current and armature current is same as I1. Okay, this is the I1. So this is one set of equation which we have. Now in the next case what they're saying is then an additional 4.6 ohm resistance is connected in series. So they are connecting an additional 4.6 ohms in series. So this is say 4.6 ohm in series. This is 0.4 ohm. Now estimate the new speed. Now in the next case, let us say the current drawn is I2. Okay. So we know that first of all, torque is proportional to N2 square. And what is the situation? It is also proportional to I2 square. So you have one equation from this, and so this is T1, this is T2. So T1 by T2 if you do, you will get N1 square by N2 square is equal to I1 square by I2 square. Okay, so here N1 square is known as 600 square, I1 is also known as 40 square, N2 square is unknown and I2 square is unknown. N2 and I2 is unknown. Now we need to get another equation for N2 and I2. So what another equation we'll be using? We will be using the equation of back EMF. Okay. So EB1 by EB2 is proportional to, because magnetization curve is linear, so EB is proportional to phi into omega. Phi will be proportional to the current, see the current which is flowing. So this is, for the first case it is I1 into N1, and for the second case it is I2 into N2. Now what is EB1 for the first case? EB1 for the first case is 220 minus what you say I1 40 into 0.4. Now for the second case, what is EB2? EB2 is, because the supply voltage is the same, okay, 220. The current we don't know, but the overall resistance is 0.4 plus the additional resistance of 4.6, which is 5. Okay. So here you know I1. So I1 and N1 is known. So I1 is 40 and N1 is 600. Okay. And this is another relation using the back EMF condition. So here also you see there are two unknowns, I2 and N2. So here you have one equation, and here you have another equation, and you have two unknowns, I2 and N2. So you can solve for it, and if you solve for it, you will get I2 current as 26.326 and N2 is 394. So in this question, they're asking you the new speed, and in the next question, they're asking you the new motor current, I2. Okay. So in this way, you can solve for these questions. So you will see in most, the 2-3 things are important things which you have to note. First of all, while you are reading the question, you should note that whether the magnetization curve is linear or whether the magnetization curve is saturated. If it is linear, then the flux will be proportional to the, for the series motor, it will be proportional to the current, field current. If it is saturated, then the flux will be constant. Okay. So this is one important thing which you have to read. And the second thing is, you will be generally seeing that we are using either the load torque conditions for solving the, we are using load torque conditions and the back EMF conditions to solve for unknowns. Okay. So in the series motor case, you will see that somehow you have to use the load torque conditions and the back EMF conditions to solve whatever is required. Okay. So this is all for this class. So if that, so here if I'll be stopping the class. Okay. So that is it for this class. So I have discussed all the 10 questions, and then also I have discussed the theory. Okay. So here we discussed the series DC machine, and then we saw the, what you say, speed versus load characteristics. Then we also saw torque versus load characteristics. Then here what else we saw? We saw the, what you say, how you can control the, what you say, speed of the series motor by changing the field current, by doing this changing in the field winding connection, or by putting a diverter resistance externally. You can also control the speed by changing this terminal voltage also. Okay. Then we saw the Swinburne's test, which is the no load test for predetermination of the efficiency. And then we saw the Hopkinson's this Hopkinson's test, which is the back-to-back test. Okay. So that is all for today's class. So I'll be stopping the class here. Okay. So I'm stopping the class.